So till now we have talked about single leader and multi-leader replication. Now let's see what a leaderless replication is. So the replication approaches we have discussed so far in this chapter, that is the single leader and multi-leader replication, they are based on the idea that a client sends a write request to one node, which is the leader node, and the database system takes care of copying that write to all the other replicas. In this case, a leader determines the order in which the writes should be processed, and the followers they apply the leader's writes in the same order. Now, some data storage systems they take a different approach and they totally abandon the concept of a leader and they allow any replica to directly accept writes from the client. So that's called a leaderless replication. Amazon used this for the in-house Dynamo system. Cassandra and Voldemort DB, they're open source data stores which have leaderless replication. They are also inspired from Dynamo. So these kind of databases, they are known as Dynamo style DBs. Now let's see how this leaderless replication it simplifies or complicates our lives. Imagine you have a database with three replicas. So in this diagram here, you have replica 1, 2 and 3. And one of the replicas is currently offline. So the replica 3 here is an offline node. And this can be due to it being rebooted to install a system update. Now in this case, in this image, the replica 3 is unavailable. Now in a leader based configuration, if you want to continue processing the writes, then you may need to perform a failover as we saw in the earlier video. Now on the other hand, in a leaderless configuration, failover process does not exist. So this image shows what happens in that case. So the client user 1, 2, 3, 4 here, it sends the write to all the three replicas in parallel. So it's sending a write to replica 1, replica 2 and then replica 3. So in this case, the two available replicas, they accept the writes, but the third replica, it doesn't accept that write. So let's say it's sufficient for just 2 out of 3 replicas to acknowledge the write. Now after a user or client has received the 2 OK responses here, we can consider that write to be successful. So the client will simply ignore the fact that this offline replica has missed the write. So this is how we handle the write operation. Now let's see how the read is handled in this case. Now imagine that the unavailable node, it comes back online after some time and clients start reading from it. So any writes that happened while the node was down are missing from that node. So if you read from that node, then you may get stale or outdated values as the responses. So in this case, as you can see, this get, if the client is doing get operation here, then this replica 3, it returns a response with version 6, and the other two replicas, they return a response with version 7. So replica 3, it's returning a stale response here. So to solve this problem, as you see, when a client reads from a database, it doesn't just send requests to one replica. So read requests are also sent to several nodes in parallel. Now the client may get different responses from different nodes. It can get up-to-date value from one node and a stale value from another. So then it uses this version numbers to determine which value is the newer one. So we'll discuss more about the version number in the next video and see how it helps in resolving the difference here. The replication scheme, ideally, it should ensure that eventually all the data is copied to all the replicas that we have. So after an offline node comes back online in a leaderless replication, so let's see how does it catch up on the writes that it might have missed. So two mechanisms are used in case of Dynamo style data stores. So first one of them is read repair. Now when a client makes a read from several nodes in parallel, it can detect any stale responses. So in the last slide, we saw that user 2345, it gets a version 6 from replica 3, the offline replica, and it gets a new version from the other two replicas. So the client will see that replica 3 has a stale value and it will then write the newer value back to that replica. So this is called a read repair process. And since this is happening at read time, so this approach will work very well for values that are frequently read. Now next one is anti-entropy process. So some data stores also have a background process that will constantly look for any differences in the data between the replicas, and it will copy any missing data from one replica to other. So unlike the replication log in a leader based replication, this anti-entropy process, it does not copy those writes in a particular order. So, and also there might be some significant delay before the data is copied. Not all systems implement both of these. For example, Voldemort DB, it currently does not have an anti-entropy process. So Without an anti-entropy process, values that are rarely read, they might be missing from some replicas, and it will reduce the durability, because read repair it only happens when the value is read by the application. Now in this image that we saw earlier, we just discussed we considered the write to be successful, even though it was only processed by 2 out of 3 replicas. But let's say if only 1 out of 3 replicas accepted the write and the other 2, they are unavailable or offline. So like how far can we go like this, in this way? Like how many failure nodes can we accept like this? So if we know that every successful write is guaranteed to be present on at least 2 out of these 3 replicas, then that means that at most 1 replica can be stale. So if we read value in that case from at least the 2 replicas, then we can be sure that at least one of them is up to date. So if the third replica is down, or let's say slow to respond, then reads can nevertheless, it can continue, and then they will continue returning an up to date value. So this is the general rule that we have. If we have, let's say, a total of n replicas, then every write, it must be confirmed by W nodes to be considered successful. And we must query at least R nodes for each read operation. So in our example, in the last slide, for us n equal to 3, because we have 3 replicas, and the W and R for us is both, there are 2 here, because we want to write to at least 2 nodes, and we want to read from at least 2 nodes if we want our read to be up to date, read to return an up to date value. So as long as this condition W plus R greater than n, this holds, then we can expect to get an up to date value while the read operation, because at least one of the R nodes we are reading from, it must be up to date. So read and writes that obey these R and W values here, they are called quorum reads and quorum writes. So you can think of R and W as the minimum number of votes which are required for the read or write operation to be valid. So this quorum condition W plus R greater than n, it allows the system to tolerate some unavailable nodes, and here is how that will happen. So in this case, for us n equal to 3, we have 3 replicas, and let's say the value of read and write nodes, they are both 2, then we can tolerate one unavailable node, and that's the ideal scenario as we just saw. So let's say if we have R equal to 1 and W equal to 3, it means that while reading, we just need consensus, or we just need quorum from one node, and while writing, we will need the OK value, a success value from all the three replicas. So, but in this case, since we are waiting for write from all the three nodes, so this quorum condition, it allows for faster reads, but it has the disadvantage that just one failed node can cause all the database writes to fail, because in this case we are waiting for all the 3 nodes, 3 replicas to respond with a success value. So if any one of them, any one of the 3 is down, then it will cause the whole write operation to fail. On the contrary, let's say if we have W equal to 1 and R equal to 3, then same, it will lead to faster writes, because we just need a success value from one of the write nodes, but it can lead to a read failure in case one node is down, because in this case, since R equal to 3, then it means we are waiting for a success value from all the 3 nodes before we can send the success message to the client. So often R and N, they are chosen to be a majority. It should be more than n by 2 of nodes, because that assumes, that ensures that the condition that we saw earlier, W plus R greater than n, it will definitely hold, and it will still tolerate up to n by 2 node failures. So half of the nodes can go down, and the system can still, it will still continue to operate while returning the up-to-date values. Now this is the case when we have n equal to 5, that is we have 5 replicas, and W equal to 3 for a successful write, and R equal to 3 for successful read. This is the quorum condition that we have here. So in this case, we can tolerate 2 unavailable nodes as shown in the image here. So normally in this case, like in all the cases, reads and writes are always sent to all the n replicas in parallel. So the parameters W and R, they determine how many nodes we wait for, or how many of the end nodes need to report success before we consider the read or write to be a successful operation.